Welcome to lecture 5 of this chapter on NOCs, on-chip networks. So this will be a somewhat shorter lecture where we will discuss non-uniform cache architectures, which will basically tell us how the on-chip network is co-designed with the cache hierarchy. And then of course we will discuss performance aspects. So what's the key idea here? The key idea is that L2 and L3 caches are very large. So given the fact that they are very large, what we have is we have the cores over here and we have a sea of cache banks. So let's call them B, C for core and B for cache banks, and there can be a lot of these cache banks. So if let's say a message needs to go from here to here via these routers, then of course it will have to pass through the links and the routers, and in this case, as we have just seen in the 4th lecture, the router delay can be substantial. In the sense, a full pipeline could be 5 cycles, otherwise the router delay could be like 3 cycles or 4 cycles. So the router delay as such could be quite high, right? It could be substantial. So that is why it takes a long time, even end to end, a lot of time is spent in routers. If it's a remote bank, as I said, if this is the core and it's a remote bank, it's far away. It could be 20 to 50 cycles or even more depending upon the size of the network and of course the congestion. So this basically means the cache access time, particularly for a large cache. So typically the word LLC is used. LLC is a last level cache. In an LLC, the access time could be fairly variable, right? And this is why we have a non-uniform cache, because all of these LLCs are fundamentally non-uniform, because the data is distributed throughout the chip and the access times are very non-uniform. Well, this number one is a problem because it induces a slowdown, but the idea is, can we take advantage of this? Well, in principle, we can place frequently used data closer to the cores. So this is something that we can do. So in this case, what will happen is that all the data that we frequently use, that will be closer to the core. So somehow it will be placed, let's say, close to this core if this core is accessing, to reduce the perceived latency. But how to do that is a separate matter. So this is what we will look at in this chapter primarily. So let us first discuss the most the simplest scheme, static NUCA, S-NUCA. So the key idea is that, let's say I have a large number of cache banks in the LLC that are organized like this in a matrix form. Each one of them is a cache bank. So the idea is, how do I split the cache blocks, or which is basically the physical address space, and map them to the cache banks, right? This itself is a hard problem, right? So give a cache block, find which cache bank it maps to. This itself is not an easy problem. And we need to ensure that the access is kind of homogenized, in the sense no hotspots are forming. It's not the case that for a given bank, let's say this one, there is a lot of contention, and the bank just to the sides of it there is no contention at all. So there are multiple ways that we can kind of split a physical address, post translation that is, into the different components. So the first would be the byte within a block. So we have already seen this, right? So the byte within a block, if it's a 64 byte block, we will spend 6 bits in this, right? And so this is essentially a log of the block size. So this is something, of course, that we should ignore. This is not important. And then in a traditional set associative cache, we had the set ID and the tag. Now what we have is, we have an additional bank ID, which is a couple of bits that we kind of reserve for saying which bank it is. Let's say if there are 16 banks, then this will be a 4-bit field, which will essentially tell us which bank we need to go to. Now there are many ways in which this bank ID can come out from a physical address. In the sense, in this case, it's in the middle. So clearly, the more we move towards the left, the lesser is the randomness. So in this case, what would happen is that we would kind of have more clustering at the bank level, which may not be a bad idea, mainly because we could possibly associate a small cache along with the bank to kind of store things, kind of store frequently accessed blocks. But Again, this is not done, but clearly there is more of clustering over here in this bank ID, and there is less of clustering over here in a bank. The main reason being that in this case the bank ID is determined first with the lower order bits, and the lower it is, more is the randomness. So we expect this approach, which is the second mapping, to be way more spread out, right? So there is no doubt about this, that the more the bank ID bits kind of move to the right, we are increasing randomness, and it will be, the accesses will be more spread out across the banks. And the more it moves to the left, we are reducing randomness, so the accesses will kind of be more clustered, with respect to a few banks. So that is kind of known. So there are different advantages for choosing different mappings. In this case, the advantage is clearly homogenization. In this case, we are trying to deliberately kind of cluster. But of course, if we look at set IDs, in this case, the sets will be distributed kind of homogeneously, which could be an advantage in the sense that even though banks accesses will be clustered, but within a bank, the sets will be uniformly, the data will be uniformly distributed across the sets, whereas in this case the banks will be kind of random. So just to repeat, the banks are random in mapping 2, but the sets aren't. So there are, so you'll see more clustering at the set level, which may not be a good idea, especially if you are prone to conflict misses. So as you can see, there are, pros and cons. It's not very clear, which idea is better than which one. So now let's come to a dynamic approach known as dynamic NUCA, where the idea is that we bring frequently used data closer to the core that is requesting it. So what we do is that we create bank sets, which are groups of banks. So let's not confuse this set with the sets within a bank. This set is different. Let's call it groups of banks. So that's possibly a better idea. So let's now clear the ink and see what's happening. So let this be the requesting core, and let it request for a bank that is actually there in this bank set, right? So as I said, each column is a bank set. So basically what we do is, if there are 4 bank sets, then we basically extract 2 bits from the physical address, right? We'll talk about the position later, but let it be 2 bits. It will tell us in which bank set we are. Then what we do is we find the bank in the bank set which is the closest to the requesting core. So it is pretty much like a perpendicular line on this bank set, and in this case this would be the closest bank, so we call this the home bank. So what we do is that we start a protocol of searching. So the basic idea is that the block that we are requesting for could be there in any bank in the bank set. So that is the basic insight, that the bank set is a collection of banks, and furthermore the block could be there in any bank of the bank set. So we basically need to search. We shall see there are several advantages, even though up front it looks like something to be much heavier than S-NUCA, but that's not really the case. So the operation of the protocol is like this: given a physical address, we map it to a bank set, which basically means that we'll have the tag, we'll then have the bank set ID, the set ID and the byte within a block. So in this case, even if there is clustering on the bank set, as we shall see, it's not a problem, because there are a lot of banks in the bank set, and we can take care of that. And it is more important to homogenize accesses within a bank. So that's the reason the set ID has more randomness. So the key idea is that once we go to the bank set, so the request goes, basically the path of the request is from the requesting core RC to the home bank. The home bank is the closest bank in the bank set. So the idea is that we first search for the block in the home bank. If we find it, we declare a cache hit, right? Otherwise we do something, and then if you are not able to find the block within the entire bank set, then we basically go to the lower levels. It's like a cache miss. So there are several search strategies, as we shall see: sequential, two-way and broadcast, and they have their own advantages and disadvantages. So let us now look at search strategies. So there are three possible search strategies. So we of course always start from the home bank, and we always check whether the block is there in the home bank or not. So the first search strategy is sequential, where we go to the second block. So we go one side, steps 2, 3, 4 and 5, and then we keep checking. If we don't find, then we again come to the other side and we keep checking. So it's kind of sequentially. First go this way and then you go that way. So as you can see, of course, sequential reduces the load on the banks because we don't have parallel accesses, but it is very slow. So what we could have otherwise is that we could have, let's come to see a broadcast access, right, where we kind of send parallel messages to all the banks. We ask all of them to check and report back. So even though this is the fastest, it does increase traffic substantially, right? I would say a big traffic plus. And it also increases the load on the banks and the bank contention substantially. So what has been found to be reasonably good in practice is the two-way approach, where we send two parallel probes on both sides, after checking the home bank. So what we do is we check one block to the left, one block to the right. Then again 2 blocks to the left, as you can see, time step 3 here, time step 3 here, right, 1 over here, 1 over here, so on and so forth. So this is the two-way access scheme, which is kind of conceptually somewhere between sequential and broadcast, and it does in a sense achieve a trade-off between parallelism on one side and latency on the other side, right? So basically, parallelism, latency is the same thing, but let's say bank contention or let's say bank accesses, which can indicate power also on the other side, right? So basically we don't go sequentially, but again we go at twice the rate of sequential, and we still end up reducing the latency quite a bit, and we don't increase the bank contention too much or the extra additional work too much, right, at least as compared to sequential. So after a hit miss detection, if there is a hit decision, then we send the block to the requesting core. So here is the D-NUCA nest, the dynamic nest of the scheme, right, D-NUCA, which is that we promote the block. So once a block, let's say, was found somewhere, so let's say that regardless of the search strategy, this is the home bank, and let's say the block was found over here, then what we do is we essentially promote the block, in the sense we move it closer to the home bank, or maybe to the home bank itself. So we bring it to a nearer bank which is closer to the home bank, or maybe to the home bank itself. So this is a process of promotion, in the sense that you are bringing it closer and closer to the requesting core, and when it is on the home bank, at the home bank, it is essentially the closest to the requesting core. So now the idea is that why is this being done? Well, the reason that this is being done is to ensure that subsequent accesses, if there is spatial locality, subsequent accesses to different bytes within the same block will have hits, and then those hits will be closer to the requesting core, right? So the messages don't have to, if this is the requesting core, they don't have to travel very far. If it's, let's say, they are close to the home bank, they just have to travel this much, which is fine. Or let's say it is better than what used to be the case. So now what happens is that in a new bank, if there is an empty block, and we can put in this block over there, if there is empty space, there is no problem. Otherwise, one option is eviction, that we evict something from a set to make way for the block that is getting promoted, or we just do a swap. So basically this goes here and that goes there. So bringing blocks closer to the home bank is also consistent with temporal locality, the reason being that the same block may be accessed again. In this case, it will be found closer to the core. If there is a miss, which means you don't find it, then of course you have to fetch it from the lower level. Now the question is, where do you place it? There are multiple options, and the different options are associated with different trade-offs. Either we insert it into the nearest bank, which is the home bank, right? or we insert it to the farthest bank and we let it get promoted over time. So the strategy of course depends on the access pattern, it depends on the quality, on the nature of the workload. So it's reasonably hard to say that what exactly is the best idea. Is it one decision, or is it some other decision, right? So this is basically dependent on what our simulation studies would say. Eviction and migration. So once a block, assume that a block needs to be evicted. So one option is to of course send it to the lower level. The other is to kind of demote it, right? So this is the opposite of promotion, it is kind of demotion. The other idea is to demote it, which is to move it away from the home bank. So if the block is over here, you demote it and move it away from the home bank. In a sense, it still remains in the bank set, but but it is kind of further away from the home bank. So we are not really penalizing the program by sending it all the way down to main memory or something, but we are increasing its access time next time. The main reason is that it got demoted. It doesn't have a high priority anymore, because in the bank that it was there, it was anyway evicting it. So we decided to kind of make it a soft eviction by demoting it within the bank set. The advantage is that this approach keeps data close to the requesting course, no doubt. Depending upon the usage and the patterns, it brings data closer. Furthermore, it gives a block multiple chances. So upon an eviction, you can move it to a bank slightly further away, or you can bring it closer. And all of these things, the search policy, which is, we looked at it, right? Either it's two-way or one-way or migration or broadcast, whatever. The search policy, locating the bank, the migration and eviction policies, as we have discussed right here, are all very important design decisions in the design of any dynamic NUCA scheme. So as of today, there are many dynamic NUCA schemes, and all of them in a sense look quite different, but they are optimized for different kinds of workload. So we can of course have more advanced designs where the private data, so data that is accessed by only one core, only by the thread that is running on a core, is stored within the bank in the tiles. So basically what happens is that if this is the core, then let's say we divide blocks of cores and cache banks into tiles, as we have seen earlier. So you can say that, look, if something is private, it's going to remain only within these banks. Fair enough. So this is something that can be done. Furthermore, for shared data, we can have the same thing as S-NUCA, where we basically just put it based on the physical address, and if it's read-only data, it can be replicated in the sense you can have copies of it in different banks. So how do you know which one is which? Well, we could have compiler support, in the sense the compiler could tell us which data is what by analyzing the program. We could have profiler support, where you basically run a test run of the program and you get an idea which data structure is read-only, which is shared, private, and so on. So of course, there are some more advantages that we can accrue from here. So we clearly know that code is read-only, right? Unless of course, it's one of those advanced programs that modify themselves, code is mainly read-only. So limited replication ensures very good instruction hit rate. So what we can do is, given the fact that it is important to kind of make the access to code instructions basically as fast as possible, the instruction hit rate is very important. The performance is very sensitive to this. So what we can do is that we can kind of replicate the code in different cache banks, and given the fact that it's read only, there are no synchronization issues. So this can be done, but replicating all the data, which is potentially read-write data, is tricky, because you have to then synchronize the replicas, and that's hard. So this is something we'll look at in the next chapter, chapter 9, with regards to maintaining synchronization. But if it's just read-only data, it can be replicated such that the data is always closer to you. So these are again part of advanced designs. We have not looked at them, but this is broadly the design philosophy that they follow. So now we'll look at the last aspect of this chapter, which is performance analysis. So how do you evaluate the performance of a network, right? How do you know that whether the network, and network means not just the network, it is the topology of the network, it is the routing protocols, right, in the network, what kind of protocols you use. It is basically the design of the router, right? It's essentially the optimizations that you use. Even things like the, the flow control policy, right? What is your credit regime, in the sense on-off credits or what? So how do you basically achieve flow control between links? So all of these things are important. And for that, there are many evaluation metrics. One, of course, is the latency, which is the easiest, which is that from point A to point B on an average, how long does it take? Or let's say between any two pairs, how long does it take? The other is throughput, which you can measure in terms of megabytes or gigabytes per second. That, let's say, the network on a whole, how much of data is flowing, or the maximum amount of data that is flowing in the network. You can look at energy or power if you wish, and then of course the area and the routing complexity. Routing basically means the process of placing these wires, right? That is known as routing. So this is a different routing, in the sense you would say that the same term is being used over and over again. Once we talked about routing in the context of finding a route, but this is different. This is placing the wires of the network. So that's also called routing in EDA. EDA is electronic design and automation. So that's what they call routing for. And the idea is that all of these things, the latency, the throughput, energy, area, routing complexity, everything, this is all, a part of the overall evaluation schema. So there are two things we can do. So one is we can use architectural simulators. So an architectural simulator does what? It basically takes as its input a program plus its arguments. It runs the program and then simulates the program on a virtual or hypothetical CPU, where of course you are at liberty to change everything. You can change the cores, you can change the cache banks, you can change the ALU schedulers inside the cores, everything, right? So this is basically a software CPU. So the idea is that you run a real program on a simulated software CPU, which may not be real. It may be something that is, something that you would like to create, right, which is hypothetical. But again, this is the right way of basically testing out a new design. You implement a design on a software simulator, and then you essentially simulate a program or several programs, hundreds of programs, or you create a benchmark suite of programs and you run them on this CPU simulator. So then of course architectural simulators could come in two types. One is that you take a program, you run it on what is called a CPU emulator, which of course does not give you all of these statistics. Basically, given an instruction, it just provides the result, but it doesn't really simulate the pipeline or on-chip network or anything. So one option is that you just execute the program, you collect all the instructions and the results. This is known as a trace, and you provide the trace to the simulator. The other is that you run the original program on some sort of a CPU emulator, which at runtime can give you the trace. It's like an online trace of the trace would basically say, look, I executed 4 branch instructions. These are their PCs. These are their outcomes. I just ran 10 add instructions or something, that PCs and outcomes. So all of these things a dynamic CPU emulator can provide. If let's say we don't want to go this way, which is slow, then of course we can go the fast way, which is we can use standalone network simulators, where we can either get data from traces, or we could generate our traffic synthetically, so synthetic traffic based, and then basically just simulate sending messages, and then we can see all of these things: latency, throughput, energy, everything. So in this case, the traffic distribution is kind of artificial, it's synthetic. So, architectural simulation, as I said, we have the program and then we run the program on an emulated CPU that provides us the traces of the network data and the addresses, which essentially tells you that, look, if this is the network, you are essentially going from here to here, here to here, here to here, and so on. We simulate the NOC, which means we simulate all aspects of it, the routers, the links, all the algorithms for flow control, and so on. And then we finally get latency, throughput, and power energy statistics. So the positive part is that this can simulate NOCs accurately for real workloads. That's the positive aspect. The negative aspect is that this is slow, right? So that's a reasonably high, reasonably strong negative aspect, that this is a slow process. So what could be a faster process is that we go for synthetic traffic generation, where instead of getting, actual information. So what is actual information? Is essentially a time and a source destination pair, right? Which saying that at this time a message was sent from this source to this destination. So now you simulate. So well, we could do that. So we could run a real program on a hypothetical CPU. We could get all of this piece of information and then simulate. Another idea would be that we create a mesh, or or any kind of a mesh like network, and then we generate synthetic traffic, which is basically the same information, but this follows a certain distribution. In the sense, you have a set of source to destination pairs which send messages at certain times. So the source, so given the fact that it's a mesh, what you can do is that you can have an x coordinate and a y coordinate. So this could be the x coordinate and this could be the y coordinate. So every source would have an x coordinate and a y coordinate, which is sx and sy. Similarly, every destination would have an x coordinate and a y coordinate, which is dx and dy. So let's now look at a few simple patterns of traffic, and then we will gradually, slowly make that more and more complicated. So the easiest traffic pattern is actually random, where from a given source we send a packet to a destination at random. So it is like random traffic simulation. This makes some sense because a randomized experiment always has some value. But that said and done, if we want something which is more structured, one of the simplest patterns is bit complement, where dx is equal to the complement of sx. So in a certain sense, it's like, sending the message far away. So that's why this is typically used to test the NOC throughput, because bit complement means that, if you are, let's say, at 1010, you're sending it to 0101, which in a certain sense is far away, right? Look at it from any angle, it's reasonably far away from you. Similarly, the yth component is also the bit complement of dy. So dy is essentially equal to the yth component of x complemented. So let's look at these. I have a small diagram over here. So if you look at bit complement and if you look at these squares, so what is this? Well, this is essentially a matrix of nodes, communicating nodes, routers basically, where the routers are numbered this way: 0, 1, 2, 3 and 0, 1, 2, 3, x-axis and y-axis. So what you can see is that in the bit complement scheme, 0 will get complemented to 3. So this is 0, 0, it will go to 3, 3, right? So then these are the ones who just kind of go far, and these ones also go far. So clearly I can't show for every cell, that would clutter up the diagram, but you get the pattern that these messages from here will kind of go all the way deep down here, messages from here will go deep down here. So this is like kind of like thoroughly stress testing the throughput of the network, particularly around the center, right? So that is why the bit complement pattern is primarily used as an NOC throughput testing device. The other is transpose, which is basically, you just swap the x and y components. In this case, dx is equal to sy and dy is equal to sx. So you just swap them. So the direction of the traffic is kind of perpendicular to the diagonal. When I show the diagram, you will see that just swapping the components, so basically means a 0, 0 swapped, essentially it stays here. And for the rest, there is some amount of movement, minor amount of movement, but for a lot of other kinds of traffic, there is, there is a lot of movement kind of, if this is the diagonal over here, we see it is perpendicular to the diagonal like this. In a certain sense, this also plays the role of bit complement. It is used as a throughput testing device, albeit in a different manner. Now again, let's go back and let's look at bit reverse. So in this case, what happens is that we treat the entire S array, which is essentially the concatenation of Sx and Sy, as one large array, and the concatenation of dx and dy as one large array. So what you do is that you just reverse the bits. So you basically say that the di or the ith bit in the destination is s2n minus 1 minus I. So this basically just reverses the bits, right? So if you actually look at it, if let's say these are the bits, you start kind of interpreting these bits in a reverse manner. In a sense, you say that the ith bit in the destination is essentially, instead of counting I from here, you basically count I from there. So this completely reverses the bits. So this bit reversal, right? So basically, why did I treat both S and D as one array? Because this is kind of easier to visualize. And then of course, the midpoint, if I do, one part is the x coordinate, other is the y coordinate. So this is typically used in fast Fourier transforms. You get to see a similar traffic pattern. So this is exactly what bit reverse is. In a certain sense, it's slightly like transpose, as you can see, but then again, here you have kind of shorter, shorter communication, and here there is much longer communication, but this is sort of looks similar to transpose, at least these two diagrams. Now let's look at a few more patterns which again are visible primarily in numerical computation kind of kernels, FFT being a major one. So this is bit rotation. So in bit rotation, what you do is, this is similar to a right shift, where essentially the n-1th component here kind of gets right shifted here, this gets here. So what happens with the 0th bit, which is the first bit of Sx, is very important. It actually becomes the most significant bit of Sy, and similarly the least significant bit of Sy becomes, this becomes the most significant bit of dy, and similarly the least significant bit of Sy becomes the most significant bit of dx. So you get the pattern is essentially the destination is formed by right shifting the source, and then finally you do a wraparound. So the values of dx and dy are nothing but dy is sy0 and then sx n-1 to sx1, which is basically in all of these right shifted, and similar is the definition for dy. So this is bit rotation. Then you have shuffle. So we will discuss, I'll discuss tornado later, but shuffle, the idea is the same thing, but instead of a right shift, it is nothing but a left shift. So all of these arrows which are going right, they in this case, they go left. So it's like a left shift. So if I look at bit rotation and shuffle, what you would basically see is that right shifting does what? It basically divides by 2. But given the fact that this is slightly more complicated than a right shift, because the LSB comes into the MSB and so on, pretty much in some cases it's not like a pure division by 2, but there is more or less a movement from, let's say, this end to this end, a movement towards the origin, right? There is pretty much a movement either down, either leftwards or downwards, or a combination of left and down, but the entire traffic is kind of trying to come towards the origin or the axis. Pretty much, if these are the axis, the entire traffic is trying to come this way. So this would typically be useful when essentially I'm trying to reduce something, in the sense the computation has finished and I'm trying to kind of bring everything close to me. The shuffle pattern, which was pretty much a left shift, will do the same. It will basically double in the other direction, which is moving away from the origin, right? You can see this front tire moving away from the origin. So this is exactly what it is doing, which is moving away. It's like spreading a computation. So that is when I would like to do a shuffle. Tornado, as you can see, I'll show you the equation, but as you can see from the diagram over here, that tornado basically means that, every cell is essentially shifted 3 places to the right. In fact, that's the way it is defined, that the y coordinate remains the same. As you can see, dy is equal to sy. But the x coordinate, basically we add a number to it and n by 2 minus 1. So pretty much, like half the distance it is shifted. So this is typically seen when we are solving differential equations in parallel on a group of course. You would see this tornado pattern. This also looks like a tornado. A large amount of data is moving to the right. So more or less that's the idea. But then of course towards the end there is a wraparound, mainly because of this percentage n. Right. So now we have finally, after 5 lectures, reached the end of this chapter. So we should celebrate. So let me quickly conclude. So modern NOCs have a complex network of nodes and links. The hierarchy is a message broken down into packets, and an entire packet flows, all the bits in the packet flow along the same route. Furthermore, we have head flits, body flits and tail flits, and the head flit is typically the one at the head of the packet. All the routing decisions are made on the head flit. A flit we may not be able to transmit in a single cycle, we have to transmit it in multiple cycles, but they have to be consecutive, and a flit is an atomic unit. So it can furthermore be divided into fits. The key issues in NOCs we saw: deadlocks, live locks and starvation. Deadlock free routing protocols are there, no doubt. They are deadlock free because they avoid some turns. This stops any kind of a clockwise or anti-clockwise cycle from forming. The router has 5 stages: BW, RC, VA, SA, ST. We can further optimize them by using a bunch of techniques, as we have seen: look-ahead routing, speculative VC allocation, bypassing, etc. For evaluating the performance of an NOC, if you don't want to use a traditional architectural simulation based method, that's also fine. You can use a synthetic traffic generator. We just looked at a couple of examples of synthetic traffic generation. So I would like to end here, and in the next chapter we will discuss multiprocessors.